So in Chapter 2, we studied groups and rings and fields, and the important thing that we're going to start off with in Chapter 3 is this idea that both Q and Q adjoin root 2, which was the set of all elements of the form a plus b root 2, where a and b were rational numbers, were fields. And so that meant they were closed under addition and multiplication. We can add elements from either set and get back an element in that same set. And we can multiply elements in whichever and get back something in that same set. And we also had additive inverses. We had an additive identity, a multiplicative identity, and we had multiplicative inverses for everything except 0. So remember, we figured out how to write 1 over a plus b root 2 in that same form of rational plus root 2. All right, so these are both fields, and Q is a subfield of Q adjoin 2. So we talk about Q adjoin root 2 as a field extension of Q. And all that means is just what I said a second ago, that Q is smaller, it's a subfield, and they're both fields. Okay, so when we talk about Q adjoin root 2 as the one that contains Q, we talk about Q adjoin root 2 as the field extension, a field extension of Q. And there are a couple of ways we can write this for notationally. One is we can write root 2 over Q. I would pronounce it over like that, but we don't mean over in a division sense. We just mean it's a field, then Q. Q is a field of it. And sometimes we want to be a little more sort of diagrammatic with it, and we want to write it in a sort of vertical way. So I would write Q as my base field, and then I'd write Q adjoin root 2 over it like this. All right, so all we're saying here is Q is a subfield, field Q adjoin root 2. So another example of this, example, is actually going to contain 3 field extensions that are sort of all combined with each other. So in this example, our base field again is going to be Q, and above it we have Q adjoin root 2, but then I'm going to make a function of Q adjoin root 2 by adjoining root 3 to it. Okay, so the 3 field extensions that we have here that are all contained in this one single diagram are Q adjoin root 2 root 3 over Q adjoin root 2, so field extension. We have down at the bottom here, we have this Q adjoin root 2 over Q field extension. And then there's a big one, this sort of top to bottom field extension where Q adjoin root 3 field extension over Q. And so we're going to be studying little diagrams this a lot and trying to figure out what we can about these different field extensions, how they're related to each other, and what we can say about them. So that's one of the main focuses for the rest of the course. So to say a little bit more about this and for you to see where we're headed, so let's out a couple of those field extensions. So Q adjoin root 2. We wrote this down a second ago, but let me write it here again. This was all elements of the form plus b root 2. A and b are rational numbers. Q adjoin root 2 root 3. Let's remind ourselves of what that was. And remember, it is a field. So I didn't say that before, but that was part of a homework assignment, was showing that I do have multiplicative inverses here. So this was all elements of the form a plus b root 2 plus c root 3 plus d root 6. In order to be closed under multiplication, we needed to allow root 6's in there also. A, B, C, and D are all rational numbers. Okay, and now we're going to contrast this with a couple more sets. So we're going to think of those in comparison to each other, but also in comparison to a couple others that we've seen. So Q adjoin 2 to the 1/3. For that set, I need to allow any rational plus any rational times 2 to the 1 plus, since I need to be closed under multiplication, I need to allow 2 to the third times 2 to the 1/3, which gets me 2 to the 2/3 terms. And then after that, so multiply anything of that form with anything else of that form. I stay in that form. I can combine all my 2 to the 1/3 times 2 to the 1/3. I can combine my 2 to the 2/3 times 2 to the 2/3 and make them into 2 to the 1/3 terms. So I can simplify into the matter what. And here, A, B, and C are all rational numbers. All right, this is a field also. We're going to just take our word for it on that. We're not going to prove it. And it's sort of different than the ones above. And to contrast even a little bit further, this one is a little bit new. We looked at it early on in the rings generated by an element section in chapter 2. And I think we did it with integers instead of rationals. But the idea here is if I take all the rationals and I want to allow pi in my ring also, I am going to need not only rationals times pi squared, rationals times pi cubed, and I really should be using different coefficients here. Sorry. Let me just fix this up real quick. Okay, so I'm going to use like maybe S0, S1, S2, S3, because these guys don't end. So when I do this with pi, there is no point at which I'm going to kind of repeat the way I did up above. So what I mean by that is if we thought about up here with the q adjoin root 2, root 3, if we thought about root 3s and root 6s and multiplying them together, we'd get a root 18, right? Which is root 9 times 2, which is a 3 times the square root of 2. And so up here, there was sort of this repetition. We could reduce back to this form no matter what we started with when we multiplied. Pi, we have no such luck. We are not going to be able to reduce back to any form. We have to just allow all possible powers of pi in our set. And so this is a different kind of beast than the ones up above, which were sort of neat and tidy, right? So let's talk about in here, like why are these different? Somehow they feel very different, but it's not quite clear how we can describe that, and that's what we're trying to figure out. So one way to classify how these are different is to say, look, I needed 2 terms, and that was it. And so I might want to think about this as somehow size 2. Versus the one below it, I needed 4 terms, right? So here, I needed 4 different terms. Or if you want to look at it over here, I needed 4 rationals in order to define in order to define one element here, I needed 4 rational numbers, so I might want to call this size 4. Q adjoin 2 to the 1/3, we might think of as size 3 because I needed 3 terms. And here, I might have some kind of idea of this is an infinite size. There is no end to the power of pi that I need now. I can have pi to the 100. I can have pi to the 5,000. Those are all fair game in this set, and none of them are going to simplify or reduce down. All right, so this is a nice way to kind of categorize these sets, and we want to think more about it and understand better what we mean by size and how we know when we're done or if we never finish. The last example. So in order to do this, in order to talk about this more formally, we need to have some mathematical rules about what we mean by this size idea. And so what we're going to turn to something called vector spaces. So we're going to study vector spaces to formalize these ideas. So there's this difference in size. What do we mean by it? And that's what we're going to be studying in chapter 3.